All right, so in this one, we're looking at two sections. The sum of unit fractions 2.4, one, the Sylvester process, and sum of unit fractions 2.4.2, which is the modern sum of two fractions, of unit fractions. All right, and then the next one, we'll do the Egyptian method. But for now, these two make sense to do together because they kind of go hand in hand. All right, the Sylvester process. Any fraction is represented as a finite sum of 1/2, a third, etc. All right, so we're looking at really any fraction being the sum of other fractions where the numerator is equal to 1. All right, the process is going to feel a little weird, but it's very procedural. Find the largest unit fraction less than the given fraction. That's the key step. And so we use a multiplier of the numerator that yields or leads to the smallest result larger than the denominator. Subtract this unit fraction from the given fraction, and we'll use a calculator to support that. Find the largest unit fraction less than the difference. Subtract again, repeat until the difference is a unit fraction. All right. The key step, obviously, is the one that has the asterisk. So we're using the Sylvester process to write as a sum of unit fractions 13 over 36. So I'll walk you through this one, and then I'll do another one on the side. Multiplier of a numerator. The denominator is 3. All right. Or I'm sorry, greater than the denominator. Right. Is going to be a result of 3. So that multiplier is equal to 3. And that is the smallest value greater than the denominator of 36. So let me just kind of show you that off on the side here, or in between, I guess. So we have 13 over 36. We're taking the 13. All right. So that 13 we're going to multiply by 1. All right, we get a result of 13. We'll take that 13 and multiply by 2. That'll give me a 26. And then we'll take that 13 and multiply by 3. That'll get me a 39. All right. This is the key part. We're looking for the largest unit fraction, or actually emphasis on the fraction part, less than the given fraction. All right. So the issue you run into here, or at least the confusing part, is that we're actually looking for the first number that's bigger than the denominator. Because if I have, I'll just show you real quick, if I have the same numerator but with a different denominator, so let's say I put in a 1 over 3, but then I increase that denominator, so a different denominator but where the denominator is bigger, you see the overall decimal value of the fraction decreases. All right. So we're actually looking in trying to find a fraction that's smaller than the unit fraction associated with 13 over 36. The 36 being the operator or the key part of this. Then we would want to look for a denominator that's bigger than that through the multiplication process of multiply by 1, 2, and 3. All right. So that gives me the 39, but the multiplier itself is 3. So it implies that the unit fraction needed is 1 over 3. All right. So whatever that multiplier is going to correspond with the denominator of that unit fraction. And so what we then do is we take the 13 over 36. It's all written here, but I'll show you how it works. We then subtract 1/3, right? We get a result, but in order to subtract two fractions, I need a common denominator. So the way to get a common denominator is to figure out what I'd have to multiply the 3 by to get to a 36. That would be 12 over 12. So 13 over 36 minus 12 over 36 is equal to 1 over 36. All right. So by telling us, or by determining that 13 over 36 minus, really it was 1/3, is equal to 1 over 36. That's telling me, just using very basic algebra, if I add 1/3 to both sides, that 13 over 36 is equivalent to 1 over 36 plus 1/3. All right, both of which would be unit fractions because the numerators in both cases are equal to 1. And we'll get into why we would care about that, right? But the key step, or one of the key steps in the solution number 2, subtracting gives you the 1 over 36, where it says stop, the difference is a unit fraction. That's important because if after subtracting these two values, I get something that had a numerator other than 1, then I'd have to repeat the process. All right. So let me just grab another example here. Let's say I want to do 17 over 25. All right. So what I do, and this it's going to be a little bit more involved. All right. I'll just leave it there. I won't flower up the language, but I take my 17, I multiply it by 1, not big enough. That only gives me a 17. My target number is the first value that's bigger than whatever the denominator is. So 17 times 2 would be 34. That gets the job done. All right. My multiplier was 2. So my 17 over 25, I subtract from that 1/2. All right, which is really, it's going to be a, not the greatest fraction in the world. All right, I don't want to multiply top and bottom of 1/2 by 12.5 to get a common denominator. So we'd have to look for the LCD between 25 and 2, which is 50. So the first fraction, I'd multiply top and bottom by 2. And the second one, I'd multiply top and bottom by 25. The old trick for getting a common denominator was to multiply each denominator by, or each fraction by the other fraction's denominator. All right, so I get 34 over 50 minus 25 over 50, which is going to be 9 over 50. All right, this is not a unit fraction. Now, I recognize and realize and understand that calculators exist, so feel free, instead of showing the stuff about getting a common denominator, to just pop it into a calculator and do it that way. All right, either way would be fine, but we need the 17 over 25. The minus of the 1/2 is equal to 9 over 50, all right, which is not a unit fraction. All right, so that means we have more work ahead of us. So what I would then do is pretend that this is its own problem. All right, so kind of off on the side, I would tackle that. Looking at my 9, I would say, what do I have to multiply by 9 in order to get to the first value greater than 50? 9 times 1 gives you a 9, times 2 gives you an 18, and so on, ... 9 times 5 is 45. 9 times 6 is going to give me 54. All right. So that gives me my fractional value. And I would say 9 over 50 is equal to, all right, minus 1 over 6. And we want to see what that's equal to. All right. So just like we determined the 1/2 by determining what the minimum number of values I would have to multiply 17 by in order to get to a value, but a denominator in particular that was greater than the one that was in the fraction. The same idea here. It took me 9 times 6 to get there, but I got there. And instead of doing the common denominator thing that I did before, I would then subtract off the 1/6. That gets me a 1/75. All right. So that's a unit fraction, so I can stop finally, right? But I got to kind of think about what I have here. So I have this being equal to the 9 over 50. Now, if I solve this equation by adding a 1 over 6 to both sides, I don't actually have to add them. That would sort of actually defeat the purpose. I get 9 over 50 is equal to 1 over 75 plus 1 over 6. That's what 9 over 50 is equivalent to. All right, so I would say 9 over 50 is the same as this sum here, which tells me that 17 over 25 minus 1 over 2, instead of being equal to 9 over 50, would be equal to 1 over 75 plus 1 over 6. Then I would just add 1/2 to both sides. Let me just shrink this down a little bit so I can fit it. All right, just a smidge. But then what I could then do would be to add 1 over 2 to both sides. And I will have determined, so this cancels here, 17 over 25 is equal to 1 over 75 plus 1 over 6 plus 1 over 2. All right, so 1 over 75 plus 1 over 6 plus 1 over 2. 17 over 25, which is what I started off with. So I know it's right. It's in unit fraction form. All the numerators are equal to 1, and it adds to the relevant value, so we're good. All right, so obviously they can be not too bad, 13 over 36, or they can be kind of crunchy. So yeah, just make sure you try to kind of have a look at that procedure and make sense of it. All right, the modern sum of unit fractions, that approach is really, I mean, ultimately it boils down to the same thing. It's just kind of dressed up a little differently. Start by using the multiplier m of the numerator n, right? That yields the smallest result larger than the denominator, which kind of sounds like what we just did. Right? We came up with, in this problem, a 2 as one of the multipliers and a 6 as another multiplier. And in the typed example, it was 3 that was a multiplier. All right. So we do that, start by using the multiplier, really just kind of finding the multiplier, and then divide the above equation, this equation, mn equals d plus constant, divide that by md, and you get n over d, which is numerator over denominator, is equal to 1 over m, which would be a unit fraction. That m value, that multiplier, is what we were coming up with over here. That's why we had the 1/2 and the 1/6. And then c over md, all right? And if not all, repeat the process if they're not all the same, all right? If they're not all unit fractions, I should say. All right, so 13 over 36, that's the example we used before. We'll do that. That's done again down here. I'll do it again up here, though. So we found the multiplier. I guess I could just kind of talk you through it and then do another one on the side. All right, so we found the multiplier of 3. All right, so that got multiplied by both sides, right, with the numerator, the n value, becoming 3 times 13 equals 36 plus 3. And then we divided out the 3 times 36 in order to create that unit fraction and simplify. I think it's probably easier, and it would probably make more sense if I just kind of took you through the whole process again. So we have 13 over 36. We need that m value, all right? So again, it's 3 times something, some value, 1, 2, 3, that has to be greater than the target number, 13, 26, 39. So that makes the m value equal to 3. All right, so using the form, n over d is equal to 1 over m. So just kind of going back to the simplified part, n over d is equal to 1 over m plus some constant, whatever the constant is, over m times d. All right, so that's ultimately the form that we're looking for. All right, so I would say my m, which is, so I'll write the formula here, m n is equal to d plus constant. All right, so this is the n, this is the d. So 3 times 13 is equal to the d, 36, plus the constant, all right, some constant c. Now, we're assuming that that's going to be equal to 3 in this case, but not necessarily. So we'll leave that as a variable. Up, I have 3 times 13, which is 39. Oops. Is equal to 36 plus c. If I want to solve for c, to subtract off the 36. And I get 3 is equal to the constant c. All right. And again, c is just standing for constant. All right. So when I set up my formula of my form, the form of my formula, I could do my m n equals d plus constant. So 3 times 13 plus 36 plus 3. Now, I showed the work here, but you could have just considered it. If it's an equation and the left is 39 and the right is 36 plus something, what's the something? You're probably going to come up with 3 fairly easily. I just realized I have a plus instead of an equal. All right, but then the next step in the algorithm is telling us to take each term and divide it by the MD value, right? So a little typo here, dividing by MD. The M value, 3, the D value, 36. Get rid of those. 3 times 36. 3 times 36. All right, so over here, 36 divided by 36 is 1. 3 divided by 3 is 1. So 13 over 36 is equal to 1 over 3 plus 1 over 36, which is what we got before. We actually did the same stuff. All right, so in using the Sylvester process, we did the same thing, except we sort of structured it more algebraically here. All right.